sometimes to store the recorded thing. Let me also start this recording, just in case that recording fails. Share again. Okay. Now we are in business. Okay, so we were here, right? So we were discussing how, we're in, last time I introduced QBF, and after introducing, we did transition systems, the formulas of transition system, Kripke structures, and how, we use labels to define behaviors, and the constraints on behaviors will be what specification will be denoting. And we will later introduce temporal logics and Booki automata as specification, so as a means, a formalism to specify properties that we want to prove for systems that are modeled as transition systems. What we are discussing now is the symbolic representation of transition system and also its behaviors. Okay, and that's what we are discussing. And we'll be using quantifiers, quantified Boolean formulas to not only describe transition systems as well as its behaviors. Okay, even though in quantification over Boolean formulas, the quantifiers can be eliminated. It gives us a compact representation for representing these things. Okay, so you need to get comfortable with both these aspects, using propositional logic to model transition systems, generally modeling things in real world, specifically with transition systems, and how we could model behaviors of transition system, both linear behaviors and branching behaviors. So that is something, and specifically we'll be using quantified Boolean formulas to do that. And so it's also important that you get familiar, acquainted with quantified Boolean formulas. Towards this end, we were doing some, I was showing some quantified Boolean formulas, so with respect to transition systems, with respect to a particular transition system, which rotated a pair of bits to the right, moving 0 to it, and that's what the transition system here captures. Okay, and then we can do, we can create formulas to, denote various things about the transition system. Okay, so if we want to see when we analyze, we do model checking, we want to analyze various states that you can get from particular initial state in one or more steps. Of course, eventually we want to model behaviors as we have defined earlier. So, so I was just starting to give you some feel for how first order formulas, specifically quantified Boolean formulas, can be used. Okay, so let's see. So let's take the first one. Okay, so here I'm just arbitrarily asking this. So are there any questions about these things? Okay, and why they denote what I have claimed they denote? Okay, what they denote. And why it is relevant. Okay, so first I'll go one by one. Okay, so this is clear?
Yes, sir.
Okay, so here I'm arbitrarily creating an arbitrary formula and asking what are the models that it denotes. But more importantly, what is it that you that it intuitively, semantically denotes is more important for you to understand. Okay, so this one denotes all states that you can reach in one step from a starting state whose least significant bit is 1. Okay, so it will be a set of states, correct? Each formula, quantified Boolean formula, will represent a set of states. So this one gives you the set of all states, successive states that you can reach, that is in one step of the transition relation. Where the initial state is, the starting state is something in which the least significant bit is 1. Yeah, so this is also an image under of this set. Right. So this one.
This is for all the arbitrary input. This equation, this formula will give the successor states whose y0 is 1.
That is right. Those states, those starting states whose successor state is is constrained such that its least significant bit is 0. Okay, by inputs I mean all the start states. Okay, that get mapped in one step to a state in which whose significant bit is 1. Okay, similarly, this one is not constraining at all. Okay, it just gives all those successive states of all successive states starting from an arbitrary initial state. I mean, yeah, from an arbitrary initial state for all possible initial states. Okay, since the initial has 2 bits. Okay, so it gives the image of all possible things. Okay.
Shouldn't the previous one be least significant bit is 0?
Correct. That's, if I said differently, yeah. I mean, that was already observed. I haven't corrected that. That is correct. Yeah. Yeah. So, I mean, the point, okay, another point that I want to make is you can use, why use these quantifiers when you can expand it out like this? But you can see the reason. So when you expand out quantifiers, so here existential quantifier can be eliminated over Boolean variables by just instantiating the quantified variables for every possible 1 and 0 values that it can take, combinations of 1 and 0, and then take the disjunction of it. Okay. But as you can see, there is a blow up, and therefore, when we want to talk about these things, that it is much more compact to actually use quantifiers. So from the point of view of expressibility, but you can also, just like you've seen SAT solvers, SAT solvers can also deal with quantifiers and, implicitly, and therefore you might be able to do it. So quantified Boolean formula can provide exponential compactness in modeling sets and Boolean functions. So I'm not going to show a solution to this, but I'm going to ask, okay, and we can do that as an exercise and come back and show me next time. I mean, it's a fairly easy thing, but I still want you to think about it. So here, if I want to, so I've already shown things, formulas that represent things about one step, image and pre-image. Okay, so what is a formula? A quantified Boolean formula that denotes the two-step image under T, starting from an arbitrary initial state. You saw one step here, correct? Can one of you say Amen? How would you characterize? What is the formula that can characterize that?
So, like there should be two T functions, right? Then only like two steps can be represented.
Correct. So, yeah. And
You can do something like there exists x1, x0, y1, y0, such that T of x1, x0, y1, y0, and T
Got it.
of y1, y0, something like z1, z0.
got it. Exactly right. Okay.
Then,
So it will be a nested existentially quantified formula. There'll be two existential quantifiers, correct? Okay. Under that. So there exists, or I mean, it is either nested, you could say, or there exists x1, x0, y1, y0, such that T x1, x0, y1, y0, and T y1, y0, and z1, z0. Exactly correct. Okay. Yeah. So that is a formula that denotes the set of all states that you can reach from an arbitrary initial state in two steps. Okay. So although I have not written it down, so let's suppose that I take okay. Let's suppose that I want to denote, I have to construct a formula to denote say, an execution sequence starting from, suppose I have a transition system with an initial state and a transition relation. Okay, this defines a transition system. So I want to construct a formula which denotes the set of all k-step behaviors starting from an initial state. Or k plus 1. Okay. Oh, this is k-step. Okay. So it's 1, 2, 3. Sk. Yeah. So I'm really want So what is a formula that denotes this one? That denotes this set, such that S naught is a state in I that satisfies I, and every step here is complies with the transition relation T. Ratnakar?
I of S naught and T of S naught comma S1, and T of S2 comma S1 comma S2 and so on, T of SK minus 1 comma
Correct.
SK.
Okay, so you get the idea, no? Sorry, mistake. Yes, you're exactly right. Yeah, so you see, this is a formula that has k plus 1 variables, okay? Whereas these existentially quantified things were representing the state that you can reach in one or more steps, which you can actually do here as well, in which case you have to quantify all these things except SK. So here, since I want to model the path itself, and the way that you model the path is by constructing a formula that has as many variables as there are states in the path. Okay, so that's how you do it. Now, yeah. Now this is a finite. Yes, this is a finite path. Okay. Now I can ask the question. So since our paths can be infinite, so maybe I'm getting ahead. Okay, of the thing. So there's the question of how you can, if your paths were infinite, how you could denote this, because my formula, any formula in propositional logic has to be of a finite size. So, but my behavior of a transition system or its execution can be infinite, correct? So how do you think that you can denote infinite paths? Maybe this is it's a little bit thought, but I will ask who's the oh, I forgot the name. Third person. Who am I missing?
Paramalai?
Paramalai. Sorry. Okay. Yeah. You see, I mean, it needs a little bit. It's a bit tough. How can, if you have only a finite state systems, okay, and let's assume that our system is finite state, in the sense that the universe is finite state. How can there be infinite paths on a finite state system? Let's assume that is finite state. That my set S, over which the transition relation and initial condition are
There's a
defined.
cycle.
Yeah?
There's a cycle.
You're exactly right. So there has to be a cycle, okay? So, yeah, I mean, you can think about it. I mean, we will get to this later on. So you can, since there is a cycle, at some point, there'll be a case such that you will, there has to be a cycle. So that SK at some point, I mean, you have to get S0, S1 up to SK, such that SK, there is an L somewhere, okay, less than or equal to K, at which, I mean, SL should be equal to SK. Okay, so those kinds of paths is how you have to characterize, okay, and you can very well use propositional logic and to model those things, okay. So and we will be seeing those things and you will see the model checking. There is two varieties of model checking that we'll be looking in this course. One is called symbolic model checking. That's what we'll start out with. And the second thing is automata-based model checking. Okay. In the symbolic model checking case, you will be using temporal logic and symbolic logic. I mean, you'll be using symbolic representation of transition systems and temporal logic to do the model checking problem. But in the case of automata-based thing, we'll be using transition systems, yes, but mainly what is called Booke automaton to express you, and we'll be using automata inclusion, okay, language inclusion to do that, and that will be the second part of our course. Okay, so let me now get here to this thing. This is an advanced exercise. Okay, so think about this. Okay, so can you construct now, as you saw, in order to construct a k-step image, you have to use k copies of the transition relation, the formula that defines the transition relation, correct? With the existential quantification. What I'm asking is, the question that I'm asking is, can you construct a quantified Boolean formula? Say, start with the two-step image, and then you can then extend it to some k-step for some arbitrary but finite k that contains only a single copy of t. Why are you interested in this? Because it's more compact, no? So t, usually, as you know, you have already seen the use of propositional logic to decide formulas in propositional logic, SAT solvers. And as I told you that it is NP complete in the size of the formula, which means the number of clauses as well as the number of variables. Therefore, if you do expand it out, so if you the more t that you will have to use copies of t, the harder it is. Therefore, but QBF can be used to make a more compact representation. So I'm asking this question: can you construct a quantified Boolean formula that represents a two-step image, that computes a two-step image, or even a k-step path, okay, that uses only a single copy of t? Here's a hint: you can use quantifier alternation, both existential quantification and for all, okay? And you can, the challenge here is to construct a formula that uses only a single copy of t. That is, think about it, and we will discuss it in the next class, okay? That's just an informal exercise for you to do, yeah? You understood the problem, no?
Yes, sir.
Okay. That's my last slide with this thing. What I want to do next is, just one moment, please. Now I want to start with okay, any general questions about QBF and generally modeling? We'll be discussing more modeling, okay, for the thing. But before I move on to doing, modeling in a more modular way, how you compose transition system, that's the subject that I'll be getting into. So I just want to ask you if you have any questions, general questions about QBF. Any questions? Okay, good. So we'll be talking now in the rest of the class, symbolic modeling, sequential code. Okay, and the way that we want, you've already seen, how we saw an example of how a code could be modeled. But we want, more interestingly, not with PC, but in general, I want to do it in a modular fashion. You'll see what I mean by modular. Okay, if you have small, for example, in the case of sequential code, if you want to be able to model the transition system piecewise for each maybe statement in your program, and then compose, or if you have two pieces of code, transition systems modeling two fragments of code, you may want a way to compose them such that you can build bigger transition system from smaller things. Okay, that's usually how systems are built. Okay, you never, as you know, you never write programs or build systems in a monolithic way. You usually use smaller systems to compose them together to build bigger systems. So similarly, if you had transition systems modeling, a number of transition systems modeling some subcomponents of a bigger system, you don't want to, and if you want to model a system which is composed of two subsystems, then if you want to be able to compose the transition system that you have constructed for the two individual subsystems, okay, in a modular fashion. And that's what we will be doing. And we'll be doing that for sequential code and for modeling concurrent systems, okay? And, and then we will see the role non-determinism plays there when you're dealing with concurrency. And then I'll talk about something about fairness constraints. That's the topic, that's the outline for today's lecture. Okay, so the modeling with program counters, although I have titled it like that is not the issue. So the main thing is, if there is a way that I can compose the transition system for this whole program from piecewise transition system corresponding to each instruction, each line of code, each construct in this program. Okay, we've already seen this thing, and we have seen a model of this. So here, I kind of was more interested in modeling in my own way. Okay, I didn't model the each line separately and the control structure. Suppose I want to do that, and I want to do it in such a way, that each instruction is modeled. Because so here, you may ask, why do I want to do it that way? Because sometimes you may want that level of detail, in your analysis. Where, for example, here, this transition system is only able to talk about what happens at the head of the loop, correct? Okay, and it kind of abstracts the entire body into a single transition in this thing. So you cannot talk about, for example, some properties that you expect to be true at each of these locations, okay? Because those locations are not even visible in this model, because that has been abstracted away. So I want to have a general technique wherein I'm able to model each line as a piecewise transition system and construct something, a transition system for the entire program by composing these things, the individual pieces of transition systems. And we will exploit the control structure that is in the program to do it. So let's get started. Okay, let's take a simple example. So I'll be introducing labels. So you have some declaration, and then there is an entry point to the program, and there is an exit point. Those are labels. So here, as I said, because I want to use a control. So by the way, there is a chapter 3 of the textbook is about modeling. Okay, and this way of modeling sequential programs, and then we will talk about modeling concurrent programs. They're all subjects of sections 3.4, 5, and 6 in the textbook. I'm following that fairly closely for your reference. Yeah. So since I want to kind of compose them based on the control structure of the program, specifically like the if, then, else, and while structure, and then I want to model it at the granularity of each instruction. This is one way to model. There are other ways to model without PC explicitly also. Okay, so I'm showing you one way of modeling, which introduces label for every at selected points in your program. So my state contains two parts. One is program variables, okay, that you know that you also need to have as part of the state, and then a PC, which is program labels, okay, a finite set of program labels that we introduce. And my state is a cross product of the set that the variables range over and PC, okay, the program locations that it ranges over. So we use this notation same on a set of variables to mean that, like a transition system, as you know, our transition relation always relates a post state, which is denoted in our convention as a primed variable, to a non-primed variable, which denotes the pre-state, the starting state. So same on a bunch of variables, state variables, means that they have the same value in the pre and the post state. We'll use this, in order to in the definitions. So we want to have a way of constructing the transition relation for the entire program, based on rules of the way that are used to construct the program itself. So we want a way to start with the basic component in a program, which is an assignment rule, and then there is if, then, else, and then there is while, correct? So we want to have a rule to construct, given that you have the transition relation for the two subcomponents, then I want to put them together, and that's what this thing shows. Okay, so suppose you had an assignment statement. X is being assigned some expression. So this expression has some state variables. Okay, so in this case, there's there are three variables, but this assignment statement is only changing X. Okay, so and then you have a pre-label and a post-label. Okay, if you want to model the control structure as part of it, so this assignment has a label which is located at, and after you execute that particular construct, you can go to some I prime. So it'll not only specify the transition relation, the change to the state variables, the program variables, as well as PC. Okay, so in each thing, C, that's the general scheme that is used to model it. It says that if at label I, program location I, if I have the statement, what is the and if I were to go to I prime, then what is the transition relation should be like. Okay, so S dot PC, if I'm at I, then S prime of X will be, S prime will be such after I execute this statement, what will it be? It must be equal to whatever the value of the expression is as evaluated in the pre-state, E of S, okay? All the rest of the variables other than X will remain the same. And your PC in the next state will be I prime, okay? The reason I'm choosing, in this case, the assignment case, it'll move to the next, it'll be I plus 1, or the label next to it. But in general, the control structure in the program can change, anywhere in the program. That's why I'm allowing for this thing. So for example, okay, so using this, since this program has only a single assignment, it consists of only a single assignment statement. So what is the transition relation for this whole thing, using this assignment rule? Okay, so it would be, my initial state will be, my PC will be at my entry point to a program. And the initial state, the values, it'll specify what my the various program variables are, okay? All of them are initialized to 0 as per this declaration, correct? You have to raise your hand, okay, if you have any questions. Any questions so far? So far, yeah.
So what exactly is I and I dash? It represents the line in the program?
It represents, well, you can say line number, or it given two labels, a pre-label and a post-label, okay? It just says what happens if I were at I and I had this statement, after which I go to I prime, how can, and this transition relation is supposed to define that, okay?
Okay,
So,
okay.
yeah.
It's before the instruction and after the instruction.
After the
Before it's
instruction.
okay.
And the assumption is that this instruction is at location I, okay? The PC location I. If it is not at I, then I'm defining the transition relation to be false, okay? So as you can see, it says, assuming I'm at I, that's when this transition relation specifies the post state if I were to execute this instruction and move to I prime. So interpret that C, which is defining the transition relation, the piecewise transition relation, to wanting to capture what I just now said. Yeah. So you agree that this captures that. So if I'm not at the start location, if this at I, then this is false. Okay, that's the way I'm defined, and you will see why I have defined it. So this is not, this transition relation is not total, okay? So it only applies to, it tells me what the effect of executing that instruction is as a transition relation. If this instruction was if this assignment statement in this case was at label I, okay? If not, it is obviously false. That's the way I defined it, yeah?
Sir, also, what's the difference between the small s and I dash?
I and I dash, this is just a schema, okay? I'm defining, I'm telling you how I will be defining a transition relation, okay? S is the actual state, okay? Let me take an example, okay? So if, for example, S is actually a state which has a lot of state variables, okay? So E in this case is X plus 1, okay? E is X plus 1, and S is whatever the variables, the values of the variables are in S, okay? So let me show this example. For example, here, what is the transition relation for this single instruction program? It is C of I. In place of I have entry. In place of I prime, I have the location after the instruction, which is exit. So for this program, since it has only an assignment statement, I can instantiate. So I'm giving, see, I'm telling you a way of constructing a transition system for the entire program in terms of these, you could call them inference rules or rules to construct, put together the transition systems that you have. This is the base case, okay? So you have seen how in a BNF, grammar is defined to construct programs. Now, how is it defined? In a recursive way, correct? Haven't you seen BNF notation to construct programs? Yes or no?
No, sir. What's BNF?
Backus norm form, okay? Like grammars, okay? You've seen grammars?
Yeah, in TOC we studied.
Yeah?
Yeah, in TOC we studied context-free grammars.
Yeah, so those grammars, how do you construct them? I mean, the language is defined as a set of rules, no?
Yeah,
And,
yeah.
yeah, so that is what, okay? Regular grammar or context-free grammar, they're defined as you have non-terminals and terminals, okay? And then you dig. I mean, so programs can be constructed by means of those. You can give a grammar to construct the programs. No? So I am having an assignment. The terminals there are assignment statements, and you will see. Oh, I have not formally introduced that program for grammar, but you will see that. Okay. And that's what I'm doing. So if I have a single assignment statement, then the transition system for that can be constructed by invoking this rule, which gives a formula, the assignment rule. So since I know the pre-label and the post-label for this thing, I can instantiate C with the corresponding things. And this C takes the left-hand side of the assignment statement and the right-hand side expression, and that's how it is defined. So, and that's how the transition system is defined. So, transition, the piecewise transition corresponding to that single assignment rule. So, if I'm at entry, then I will move to the post-label exit, and the rest of the middle conjunct here specifies what the values of the program variables are in the post state. Okay, it says that the x in S prime will get assigned x plus 1, x one increment of whatever the value of x is in state S, and the rest and y and z remain the same. Okay, if you expand this thing out, it comes out as S prime of y is equal to S of y, S dot y, S prime of z is equal to S dot z, because y and z don't get changed. Did you get it?
Yes, sir.
Yeah. So So given this program then, so now suppose you have a program which has two statements, okay, which are composed using the sequential composition operator, semicolon, okay? So I want to be able now to construct the transition system for this entire program using the transition system that you would have constructed using the assignment rule for each of these things, okay? So what I do is I now introduce labels at every, for every line in the code. So in this case, there's an entry point, then you have a statement, and then there is a intermediate variable, okay? An intermediate, PC corresponding to the second, and then there is an exit, okay? So now, how do I, so I will define how you construct the transition system. So this is a systematic way of constructing, okay? I mean, what I did in the previous thing was I used my own cleverness in constructing the model. Here, I mean, most of these tools, model checking tools, have a front end, which given either some representation like a program, it constructs a transition system internally. Okay. What I'm describing to you now is how you can construct that in a systematic fashion. Okay. In an automatic fashion, like a compiler. Okay. Which takes a program and constructs a transition system for that program by walking through the syntax tree, the abstract syntax tree for the program. That's what I'm showing you by giving rules for each of the each construct that are used in the program. Now here I'm showing I showed you for an assignment rule, which is the base step. Now I'm showing you how to construct a transition system for a program that which uses two fragments of code which are composed sequentially using the semicolon operator. Okay, so I go from here and I introduce labels for each of the intermediate labels for each of the statements in the program. Now I'll be showing you how to construct the transition system for this program by giving a rule corresponding to the sequential composition rule, which takes two which uses the C is, you can say, is the transition system generator. Okay, which I'm defining recursively here in terms of the various constructs that I use. So a program, and I'm taking a simple thing which has assignment statement, a composition, a sequential composition statement, and if then else, a conditional statement and a while statement. Okay, I mean, maybe I should have introduced the program first, my syntax of the program, but I'm assuming these are the three constructs that I have. Assignment statement is the base statement, and if then else statement, and a sequential composition statement and a while statement. And the C is a recursive rule which says how to construct, how to compose the transition systems that you have already constructed for the components. So in this case, so that's why now given two pre and post labels and my command, which is now composing a labeled program, which is constructed by sequentially composing two commands, okay, command 1 and command 2, with a intermediate label introduced to the command. Okay, I and I prime are the entry and the exit for the entire program. Okay, so I do this by constructing, so by recursively invoking C on command 1 with the pre-label as I and the post-label as I enter, because a sequential command, how does it get executed? After when you start with I and you execute command 1, your control goes to I enter, and then you get then you execute command 2, and then your control goes to the exit point. So this is done using a disjunction. So if you're at I, you take you execute command 1 and get to I enter, right? So and that is given by by invoking the transition system generator on command 1, okay, with the post label as I enter. Or you can be at I enter. Now this program, which is composed with two commands, where can you be? You can either be at the entry or you can be at the intermediate label. If you're at the intermediate label, then you follow as per the transition system constructed for command 2. Okay. Otherwise, it is this thing is false. So TSS prime. So using this, now I can construct the transition system for this composed program, okay, by exactly instantiating the sequence rule. And that's what I've done here. And I've done it once for x is equal to x plus 1. Okay. So here, by instantiating I'll instantiate I with entry, I prime with, I with entry, and I inter with L. Okay, I inter with L, and and the other one is once again I invoke C with I inter and I prime. So when I do that, I get this as the transition system, which is a disjunction of this thing. So what does this thing say? See, when I'm executing this program, this program, I'm either at entry point or at L or at exit, okay? So if I'm at entry point, then my next state is as per the execution of x plus 1, I'm at L, right? So in a program, when I have PC, what I have is I can be at one of these entry points corresponding to the each individual statement. That's what it's saying. So either I'm at an entry point, in which case I will execute the statement, the command at that point, and then I go to L. Here, this is L, okay? And this part captures the effect of executing x plus 1. Or I'm at L, in which case I will do this and come to exit. So this captures the transition system for this program. And since PC is ranges over these program labels that you introduce for every line in your code. Okay. So are you convinced that this captures the transition system for this program?
Yes, sir.
So what does this capture actually? Let me ask you. So Paramalai, what does, okay, so, there is, okay, explain to me. So this, I'm saying, okay, so this captures a single, the transition relation here, I'm claiming it captures the execution of a single step of the program. Single step, when the control is at a particular location, correct? That's what it is. It is capturing. Okay. So, and since the program labels that I introduce are ranging over the various control points in the program, so it can be in one of those locations. For each of those locations, it is giving what happens when I execute a single step at that location. Now, there is a, yeah, so are you, are you with me on that?
Yes, sir.
Okay. So that's how I do. Now I will tell you how to construct a program, a transition system for a program that has an if then else structure. So how do you think you will have to do this? So I want to specify a general schema, general rule for constructing a transition system for this entire if then else statement given the piecewise transition relation for that represents the effect of executing the then part and the else part. Informally tell me, how do you think, what should that rule for if then else should be like? I'll show you in a moment. Paramalai?
It will be like x less than or equal to 0 implies x is equal to x plus 1. We can model it like that using implies statement.
Yeah, so if that is true, then I'll have to use the rule, okay? The rule that is C on this command, okay? The command that occurs as the then part, and then get the transition system. If this the condition evaluates to false, then I'll have to use the transition system, okay, constructed by that C, the rule, that is captured by C by invoking that C on this part, right? And that's how that is stated. I mean, before I do that, I'll have to introduce the intermediate labels. So this control structure, starting from entry, and this is exit. These are the labels for the entry and the exit. So I'll have to introduce a label for this command, the then part of the command and the else part of the command, okay? Because that is where you can go to. So I'll either go to L1, so L1 is the location, the PC location, the pre-location for the then part and the else part. Given that, once I introduce those intermediate locations, then I have a conditional loop, which tells me how to construct the transition system for this if then else statement. So there's a little bit of there's a blank space missing here. Okay, so this says given an entry and an exit PC label for this entire program, which is constructed from two commands, command 1 and command 2, being used in the then and the else part of a if then else thing. This is how you construct the transition system. So if I'm at I and the condition is true, condition as evaluated in the pre-state is true, am I? Then S prime of PC will be L if. I'll come here, control goes here. And since the execution evaluation of the condition does not affect any of the statements, I keep all my variables the same. Correct? Or I could be, if I am at I, and if C evaluates to false, then the only thing that happens is I will move the PC to else part. Okay, that is 1. Okay, so that is what the first disjunct here tells me what happens, the move from the control moving from entry to either to the then part or the else part. Okay, so if I'm at PC is an entry, then either the next state should be such that I'll either go to only PC changes. Okay, the PC control goes to I if or I else, depending upon whether C is true or C is false. Or I could be in this program, I could be at this location, the then part of the location. Then I'll have to, the transition relation will have to behave as per what C says, in C invoked on the command 1 with the pre-label as LF and the post label as I prime, which is the exit of this program. Because after you execute x equal x plus 1, you will, with the then part, you will come to exit. That's why, if I'm at I, this is what I do. If I'm at IF, then I will execute the command 1. Which means that I'll have to generate the transition relations as per executing command 1, and I go to I prime. If I'm at IELTS, then I will go to, I'll have to do as per the transition relation generated for command 2, and I'll go to I prime. So when instantiated on this labeled program, which gives all the intermediate labels, then this is what I get. So my transition system corresponding to this whole program is now, like I've constructed recursively. So if I'm at entry, then I'll either go to L1 or L2, depending upon this condition, which is x less than or equal to x, if s dot x is less than or equal to 0. So important to consider that this condition has to be evaluated in the pre-state, okay? So that's why I'm tagging s dot x, okay, in the thing. So if it is if negation of this thing holds good, that is s dot x is greater than 0, if that is the case, then all I do is change the PC value to L2, which is the else part, and there's none of the variables is changed. Or I could be at L1, in which case I have to do x equal x plus 1 and get to exit. Or if I'm at L2, then I will do whatever the transition relation as per the C. So when I recursively invoke, this gets then translated into, so I'm, if you expand the recursive invocation of C, this is what, you will get, okay? Any questions here? Notice how this thing is defined. So this is still only a single step execution of the thing. So if you want to capture the single step execution of this program, but the transition relation is allowing for the possibility that my control can be in any one of the intermediate locations, okay, or at the entry and the exit point. And for each of them, it is capturing what happens if the entry is at that location. Okay. By the way, so you remember that we had put this constraint that a transition relation has to be total. Correct? Is this transition relation total?
Yes, because we are taking like each like set of states is finite, right?
What do the others think? I've already given you an answer. Yeah, I say it is not total. So in that sense, this is a bit of a violation. I mean, you're right that, the control can only be in one of those locations, either at entry, L1, L2, or exit. Okay. But if it is an exit, have we specified what should happen? What does it happen? See, I've specified if it is entry at L1, at L2. There's no disjunct here corresponding to where S dot PC is equal to exit. So what will this transition relation evaluate to if S dot PC is equal to exit?
It can stay in the exit state itself. Rightly, it didn't accept any exit status.
Yeah, I mean, so what it will happen is that this will become false. So if
Yeah.
S dot PC is equal to exit, this is false. S dot PC is not entry. So the first two conjuncts will be false. The third disjunct will be false because S dot PC is L1 and L2. So it has a missing disjunct corresponding to what exit is. So it will be false. So you have to say what happens. You have to, so in that sense, I'm violating, okay, my own convention that I had imposed. So this is a transition relation. It does construct a transition relation for this thing, but it's a non-total transition relation for terminating programs because it does not do anything for exit. So how will you fix that? Amin?
Something like a self loop can be given, right?
Yeah, how will you capture that? Okay, so if I'm at exit,
S dot PC equal to exit and
yeah,
S
so they
dash
should
PC
have it.
equal to-
Yeah, S dot PC, if it is exit, then nothing changes, same, and S prime dot PC is equal to exit. Okay, so you will have to have another disjunct here, correct? Okay, then you will follow that convention, okay, that we had. Now that is kind of deliberately left out here because you could, I mean, if you want to make it total, then you will have to use some convention. That's not the only convention that you can use. I mean, you can choose to use different conventions, but that is the point. That is the subtle point, okay, that I'm making a note of. Yeah, is that clear for all the rest of you?
Yes, sir.
Okay.
Sir, also
Yes.
one more thing. Yeah, a few days before I read it in the book that there the transition relation is mentioned as left total. It's not given as a total relation.
No, it's left total means that. Yeah, but even if here it's not even left total, no? So yeah, it's not even left total.
Yeah, okay.
Yeah, I don't know. I mean, I would go back into the book and then see this is not even left total. Okay. So if they have a provision, so maybe I have missed something. Then maybe one thing as an exercise you could do is we can all go back into the thing and then this is not even left total. Okay. If this is how, I think this is how they've defined it there. I have made slides, by following that book. I mean, whatever is in that book. So either they have, okay, I don't know if they have this. I have to go check with the book. One other way to fix is to have a skip kind of a statement here at the very end. Okay. Is there what is there in the chat? Yeah, I think so. Right total. I mean, I would say it is subjective because then that is not even required. Okay, it is not required that it has to there has to be some pre-state for every post-state. Okay, that's why it has to be left total though. Okay, so for every pre-state, yeah. It has to be the thing. So another way to fix it is to have a skip. Okay, use the convention that I'll have a skip statement, and the skip statement will do exactly what I just now said. Okay, that it'll just skip and then it keeps has the effect of doing a self loop. Now I don't know. That is not exactly what skip in some programs do. It'll yeah, but if it's the exit, then you will have to remain at the exit. So that convention has to be somehow enforced. Now, I just noticed that it is not enforced, and therefore I made that observation. So how exactly it is handled in the book is not clear to me, but let's assume that that's how we will fix it. Okay.
Yeah. Okay. Sir. Okay.
Yeah. So now the last remaining construct. Okay. How do I? Okay. So this thing for this program, then you will have this. Okay. So yeah, this is the transition relation that you already saw. So I want to introduce the notion of a symbolic execution. You can actually, like we said, so this is the formula which corresponds to kind of it denotes a path, right? Starting from any of the initial states and that you get, by if you execute an execution sequence that is of length 2. Yeah. So you can actually plug this and then you can expand it out. So then you get a big formula. Okay. So for each step, and then you finally get, and after simplification, you get this big formula, which has 3 states: the initial state S, S prime, and S double prime. Okay. So yeah, I mean, you could use this, expand this out by actually constructing these formulas by making copies of T to various variables, and then you can expand this thing out. Yeah. I mean, that's the equivalent of, I call it as symbolic execution because this formula represents a whole set of executions. Okay. So not just a single run from a specific initial state, but rather the set of all runs starting from any one of the initial states. Yeah. Did you get it? Okay. So what remains is, in the rest of the things, I will show you the while thing. Yeah. So Paramalai, so can you give me a hint as to how you could make a rule, define C rule corresponding to while loop? Let's assume that I introduce an intermediate label. Okay, there is an entry label and an exit label, and I introduce 2 intermediate labels, one for the beginning of the body and the other one for each instructions in the body, L1, L2.
So the idea here is,
Yeah.
if
The general idea. Yeah.
if the expression is x less than 10, the entry expression is true, then
Yeah.
we move the program label to the next state, L1.
Correct.
And from L1 we move to L2, and from L2 we again move to the entry state, or the while state. We have to be again in the while, right?
Correct. But is it the
Also, if that like if x is greater than 10 means go to exit.
Yeah, that is one thing. If x is greater than or equal to 10, I mean, if the violation, if the exit, entry condition is false, then you'll have to go to exit. So that is there. Okay. So otherwise, you will have to go back to L1, not entry. Okay. I mean, you could go to entry. You could go to entry, but then, yeah, you could go back to L1, executing the beginning of the body. Okay.
No, but if we go to L1, it will not check the condition, right? Every time the loop runs.
That checking of the condition. No. Yeah. So you're right. If indeed you want to do that. Let's see, there are slightly different way of defining it, okay? You see, because, so you are either at entry, okay? If you're at entry, see here, you can be at either at entry, or if you're at entry, you go to L1, okay? See, the thing is, you don't have the, you have to, okay, so there's one thing that I should have said because I introduced the example here, but this while rule will have a body, okay, which I don't know. I mean, I have to define just in terms of body, not in terms, yeah. So you're right that you could have done that like that, but now I will, if I have to recursively define, I mean, use the transition relation that I generate from, I mean, either I'm at the beginning of the body. So there is one transition from entry to the beginning of the body, okay? And then one transition from entry to the exit. Now, the other transition is from beginning of the body. Let's suppose I don't want to look into the body because I want to recursively use this rule, okay, to the body. So then from the beginning of the body, I will go back to, I mean, you're right, okay? Yes, so you go back to entry. You're right, man, okay? So you said that, so then you repeat the while loop. You're exactly correct, okay? I was momentarily confused, yes. So that's exactly how it is defined, okay? So you go back to, so after executing the body, you go back to the I, which is the entry of the while loop, yeah? Entry of the while loop. I think I momentarily got confused because the entry is not your beginning of the program. So in this case, there is no other statement and therefore it is entry. But if it is, yeah, so otherwise you would be composing it in. So the entry is here corresponds to the beginning of the while loop. Therefore, after executing the body, you will invoke it and then you go back to the beginning of the entry of the body. You're exactly right, yeah? So, and that's what you get here. When I instantiate this, using this rule, this is what I get. Okay, so I want to stop here. Okay, you know, so you could, you know, next what I will get is how we model multi-threaded programs. Okay, and that we will take up next time. And I think this is a good place to stop and then take any questions that you might have.
Sir, I have a general question.
Yeah.
Is this kind of model checking is really used in industry, like checking the program line by line? It seems like a tedious process.
All I'm, see, there are 3 steps. I go back to the thing, okay? Now, you will have to first generate the model. We are still only discussing how you generate transition system models from system description languages or even programming languages, okay?
Yeah.
Now,
okay.
Now this generation, so let's talk about generation. I'm only talking about that, yeah? Now this generation is linear in the size of, I mean, if you were to implement the C, what you get is it's linear in the, I mean, generation itself is linear in the size of the program. So let's talk about, you know, I'm first answering the, I mean, you asked about model checking, okay? We have not got into model checking problem. I'm only telling you, describing to you how I'm able to generate a model, okay? In a recursive, if you were to write a program, it's a front end of a model checker, okay? How you analyze is different. So here, I mean, when I say the transition system, I'm trying to construct a transition system for every construct in the program. And so it is as big as the size of your program here, no? It's linear in the size of the program.
Yeah. I momentarily got confused that like we are only defining transition systems for this particular code, yeah? But we have generalized the while rule and if rule.
That's
and all.
right. That's right.
Yeah.
So,
So any
both-
program can be
yeah,
modeled.
both in terms of time, generating this is also linear in the structure of the program. Okay, it is the number of constructs. By linear in the size, I mean the number of constructs you've used.
Yeah. Okay.
And then you can see that what you have is, and there is a label. When I introduce this label, I mean, there is one label for every instruction. I mean, for every instruction in the program. Okay, so the number of disjuncts will be linear, correct? And the size of the program as well. Now, what you can ask is, if the way that I want to, we have not even got into the part of where, given this model, I'm just talking about how you generate it systematically. Given this model, if I were to do the symbolic execution that I showed, which in the case of while loop will end up being like almost executing a program, okay, then it will not scale, okay? But that's not how we do, okay? That's not how we do. So your question was probably leading to that, okay? So I have separated the two, model generation, and you can ask about, oh, this model generation thing is it scalable? Because this is like compilation, okay? It's only working on linear in the size of the program, okay? But now you can ask, how do I analyze this? See, because in the case of while loop, I'm going back to the entry of the while loop. If my analysis method will require me to unwind the loop, then it is going to be a problem, okay? Now, what I will do is there are techniques that you can do where you don't need to literally unwind it, okay? And why that's the case. Maybe in the extreme case you might need to unwind it, but even then you won't be unwinding it, at least in the symbolic model checking method. You will not be unwinding it on every possible input, okay? But you will be carrying along whole set of states, okay? So that's why, so you will be manipulating symbolic formulas, each of where that formula itself represents a whole bunch of states, okay? And therefore, the effect of symbolic execution will not have to degenerate into just unwinding the loop, okay? That in a lot of cases, you can get that effect, okay? So that part of your question was a very astute question, okay? I mean, the only way that I can do while loop, is it by unwinding it? That is one way, okay? But even there, you should, I should, point out that I'm doing it symbolically, okay, as formulas, okay? In symbolic, it's formulas, or in the case of automata, it will be language, okay? So when I do language inclusion, language intersection, etc., on infinite languages, I'm taking automata and then doing operations on automata, correct?
Yes,
Not
sir.
exactly
Yeah.
unwinding the automata, okay? That's the same kind of a technique that we will be using, yeah?
Yeah, okay, sir.
Yeah, so that is why it is not as problem. But in the worst case, it is p-space complete, okay? That we will see, okay, why it is p-space complete, yeah? The worst case is it is still p-space complete. But the technique is not just running every, enumerating every execution, okay? That will not scale. even for reasonable systems. Yeah. So if you're using symbolic, the algorithms will manipulate formulas. Okay. If it's automata, it will be operations on automata. Okay. That you will see we'll be doing. Yeah. And then eventually reduce it to one of checking inclusion of language in the case of automata. In the case of symbolic thing, it will be checking implication between two formulas is what we'll be doing. Yeah. And we'll see that when we get to the third part. I'll go by first, I'm discussing the modeling part. Next, I will introduce logic as property specification language. Third, I will get to algorithms for doing model checking. Yeah, but these are good questions. Okay, and I'm glad that you asked. Any other questions? Okay, if there are no, then I'm going to stop here. I'm going to stop sharing.